All right, we are about to go on a journey to literally the coldest possible place in the entire universe. This is a point where the rules of physics, the ones we think we understand, they start to get a little weird. They start to warp and break. We're talking about the ultimate chill, absolute zero. I mean, we all know things can get unbelievably hot, right? Think about the surface of the sun. But what about the other way? Is there a bottom to the temperature scale? Is there a point where you just flat out can't get any colder? Well, the answer is a big, definitive yes. And that absolute bottom limit, that's what we call absolute zero. And you gotta understand, this isn't just, really cold. It's a fundamental property of the universe itself. It's the theoretical point where you've sucked out every last bit of heat, and everything, all the little particles, should, in theory, just stop moving. Completely. So let's put some numbers on this, shall we? Absolute zero is minus 273.15 degrees Celsius, or if you're thinking in Fahrenheit, a truly bone-chilling minus 459.67. But honestly, for scientists who work with this stuff, the scale that matters is Kelvin. It was actually designed with absolute zero in mind. For them, 0 Kelvin is absolute zero. No messy negatives, just a hard stop. The end. Okay, so we've got the basic idea down, right? There's a cosmic floor to temperature, this point we call 0 Kelvin. But what does that actually mean? And, maybe the most important question of all, can we ever actually get there?
And here's where things get really interesting. Here's the big twist. Even though we know exactly what absolute zero is, it's physically impossible to ever reach it. The universe has this strict, unbreakable rule. You can get ridiculously close, like mind-bogglingly close, but you can never actually touch zero. So why not?
Well, the cosmic rule that says, nope, you can't go there, is called the third law of thermodynamics. The best way to think about it is like the universe's ultimate speed limit, but for cooling. It sets a very, very clear boundary, and it has some really profound consequences for how all matter behaves.
So this is the official statement from the guy who figured it out, German chemist Walther Nernst. And the key word here, the one you really need to latch onto, is entropy. Entropy is basically a measure of disorder or randomness. So to get to absolute zero, you'd need perfect order, zero entropy, zero disorder. And what Nernst's law tells us is that you just can't get there in a finite number of steps. It's like you're running a race where the finish line keeps moving just a little bit farther away every time you take a step.
Okay, here's an even better way to picture it. Imagine you're trying to cool a room by shoveling heat out of it. Sounds weird, but stick with me. At first, it's super easy, right? Your first few shovelfuls get rid of a ton of heat. But as the room gets colder, there's just less and less heat left to grab. Each new shovel you take removes a smaller and smaller and smaller amount of heat. So to get that very last final little bit of heat out of the room, well, you'd need an infinite number of shovels. You'd literally be shoveling forever. But you know what? That's only half the story. The laws of thermodynamics are just one part of it. There's an even deeper, even stranger reason we can never reach absolute zero. And for this one, we have to dive into the truly bizarre world of quantum mechanics, a place where atoms simply refuse to stand still. So in our normal, everyday world, what physicists call classical physics, you'd totally expect that at absolute zero, atoms would just stop, right? They'd be perfectly frozen, perfectly still. But quantum mechanics comes along and says, nope, not gonna happen. Even at the absolute coldest temperature imaginable, those tiny particles are still jiggling. They're still vibrating. They are fundamentally incapable of being completely, totally motionless. And the reason for that is the famous Heisenberg uncertainty principle. And it's so important to get this. This isn't about us having bad measuring tools. This is a fundamental, baked-in rule of reality. See, if an atom were perfectly still, its momentum would be exactly zero. You'd know it perfectly. But the principle says you can't know both a particle's exact position and its exact momentum at the same time. So if you knew its momentum was zero, its position would be completely unknown. It could be anywhere. The universe just forbids that paradox. So to solve it, the atom has to keep moving, just a little bit, forever. And this leftover energy, this energy from that permanent quantum jiggle, has a name. It's called zero-point energy. It is the absolute rock-bottom minimum amount of energy a system can possibly have. And you can't ever get rid of it. It's like the universe's own background hum, woven right into the fabric of space-time. And this isn't just some weird theory. It has actual real-world consequences you can see. Take liquid helium. If you cool it down, and I mean way down, to just a tiny fraction of a degree above absolute zero, it refuses to freeze. The zero-point energy of its atoms is just too strong. They jiggle around so much they can't lock themselves into a solid crystal. So it just stays a liquid, flowing right there at the very edge of the coldest temperature possible. How wild is that? Okay, so you might be thinking, if we can't actually get to absolute zero, why even bother trying? Great question. And the answer is because getting incredibly, unbelievably close has opened up a whole new universe of bizarre quantum phenomena. We're talking about entirely new states of matter that literally don't exist anywhere else. Let's start with superconductors. You take certain materials and get them extremely cold, and something amazing happens. They completely lose all their electrical resistance. Zero. Which means electricity can just flow through them forever without losing a single bit of energy. It's like the perfect electrical wire, something that shouldn't be possible. And then there's superfluidity. Remember that liquid helium that wouldn't freeze? Well, when it gets cold enough, it becomes a superfluid. This stuff flows with absolutely zero friction. It will actually climb up and over the walls of its container. It seeps through cracks that are basically atom-sized. It's a liquid that genuinely seems to defy gravity. But maybe the most exotic, the most mind-bending state of matter of them all is something called a Bose-Einstein condensate, or a BEC. This is what happens when you cool a cloud of atoms down to just billionths of a degree above absolute zero. They just stop being individual particles. They lose their identity and merge together into one single massive quantum wave. Yeah, you heard that right. In a BEC, you don't have a collection of atoms anymore. The lines between them literally dissolve. They all start acting in perfect unison, as if they're one giant superatom. It's one of the only times we get to see the spooky, weird rules of the quantum world play out on a scale that we can actually observe. And look, this isn't just some weird science experiment for the fun of it. This whole quest for the ultimate cold is opening doors to technologies that are absolutely going to shape our future. We're talking everything from quantum computers to exploring the deepest, darkest secrets of the cosmos. And you know what? We have gotten so close. Right now, up on the International Space Station, NASA's Cold Atom Lab has managed to cool atoms down to just 100 picokelvin. A picokelvin. That's 1/10,000,000th of a degree above absolute zero. That makes it, without a doubt, one of the coldest spots in the entire known universe. So why go to all that trouble? Because this cold toolkit is what lets us build the future. We're talking about the foundation for fault-tolerant quantum computers. We're talking about atomic clocks so ridiculously precise they wouldn't lose a single second over the entire age of the universe. We're talking about sensors sensitive enough to map a planet's gravity from orbit, or maybe even finally get a hint of what dark matter is. It's simple. The colder we can go, the more powerful our tools become. So when you think about it, absolute zero isn't really a destination. It's more like a gateway. Yeah, it's an impossible limit we can never reach, but in chasing it, we've unlocked these incredible new states of matter and the technologies that are going to define our future. Which, it leaves you with one final big question, doesn't it? If the coldest places in the universe are hiding all these secrets, what else is lurking out there at the other extremes of reality?